Hi, welcome to Chemical Formulas Review Part 3. My name is Dr. English, and today I'm going to be talking about naming binary molecular compounds. So I'm going to provide you with a little review of covalent bonding. We're going to look at what a molecule is one more time. We're going to look at the relationship between an empirical and a molecular formula. We're going to understand the prefixes that we're going to use to name these binary molecular compounds. And finally, at the very end, we'll go through the process of how to name a binary molecular compound and then do a bunch of examples. A little review of covalent bonding. So let's consider the water molecule, which has a formula of H2O, one oxygen, two hydrogens. When a water molecule forms, a hydrogen atom comes in and shares its valence electron with the oxygen, and then another hydrogen atom comes in and shares its valence electron with the oxygen. So what's generally happening during this process? Electrons are being shared between the nonmetal atoms, and stability is achieved through completed octets. Now remember, the electron configuration for hydrogen as an atom by itself is just 1. When it shares its valence electron with the oxygen, it now has an electron configuration of 2. And this is the more stable form of hydrogen. Oxygen, we look at the same thing. The original electron configuration of an oxygen atom before bonding with the hydrogen atoms is 2, 6, with the 6 referring to oxygen's valence electrons. When it shares its valence electrons with the hydrogens, it now completes its octet and has an electron configuration of 2, 8. Which is much more stable as it mirrors the electron configuration of neon. So let's go over what a molecule is one more time. So the definition of a molecule is two or more atoms of either the same or different nonmetal elements covalently bonded together. So we're going to be sharing electrons. So an example of this might be something like carbon monoxide, which is just CO. Another example could be diatomic nitrogen. So here's our little image of nitrogen from periodictable.com. So if I was to do the structural formula of it, it would just be two oxygens triple bonded to themselves, or just the general formula of that, the molecular formula, is N2. And another example might be something like carbon dioxide, so CO2. So in each of these cases, we have two or more different or the same nonmetals coming together to form a molecule. Remember, we can also talk about monatomic molecules, and mono meaning one, atomic meaning atom, molecules. What do these refer to? Well, they refer to the noble gases. So some examples of monatomic molecules could be helium or argon or krypton. Now really quickly, let's talk about the relationship between an empirical and molecular formula. So an empirical formula is defined as an ionic or covalent compound that's in the simplest whole number ratio of atoms of the elements in a compound. So in other words, you can't reduce anything down even farther, and we'll go over an example of that in a minute. Empirical formulas can be different than a molecular formula. A molecular formula is the actual ratio of atoms in a molecule of that compound. Now remember, if you're talking about a molecular formula, you're talking about a molecule, and a molecule has covalent bonds and it's made up of nonmetals. So molecular formulas do not describe ionic compounds. So let's look at a molecular formula. Lactic acid has a molecular formula of C3H6O3. Now that's the molecular formula of lactic acid. So in other words, if I wanted to get a molecular model kit and build a molecule of lactic acid, I would need 3 carbons, 6 hydrogens, and 3 oxygens to put it together. The empirical formula of this particular molecule would be the most reduced one. So what I would do here is I'd say, all right, if I want to do the empirical formula of this, what number divides evenly into 3, 6, and 3? And if you said, well, 3 does, Dr. English, you'd be right. So if I divide this 3 by 3, and this 6 by 3, and this 3 by 3, I would get the empirical formula. So the empirical formula of lactic acid would be CH2O, with assumed ones being down by the C and the O. Now, if you look at that, you'd say, okay, that's the empirical formula. I could multiply everything here by 3 again and get back to my molecular formula. But what if I said, well, let's look at methanol. And if you think about methanol, and remember your organic chemistry, you would say, all right, methanol. Meth means 1 carbon, and that Al ending means an aldehyde. Aldehyde. And if I quickly drew out the structure for methanol, I'd say, all right, a carbon, it's got a double bonded oxygen because that's the aldehyde. Carbon has 4 bonds, so that's got to be a hydrogen here and a hydrogen here. And if I was to write out the molecular formula of this, I'd say, well, that's CH2O. But wait a minute, there's something interesting here. This methanol has a molecular formula that is the same thing as the empirical formula of lactic acid. Therefore, CH2O for methanol is both the empirical and the molecular formula. Lactic acid is a molecular formula, not empirical, because I can divide it down to smaller whole number ratios. So molecular formula for lactic acid, empirical formula for lactic acid. On the same type, one more time, for methanol, CH2O is both the empirical and the molecular formula. So what is a binary molecular compound? Well, bi means 2. Molecular means basically nonmetals and covalent bonding. And it's a compound, so it's going to be 2 different nonmetals coming together. So here's some examples of some binary molecular compounds. Nitrogen dioxide, which is this red substance right here, and dinitrogen tetroxide, which is this lighter color over here. So these are both examples of binary molecular compounds. Another example is something like PH3, which is called phosphorus trihydride, also known as phosphine, and is contained in the red tips of matches. And then finally, another binary molecular compound is carbon monoxide, which is a compound that is released from combustion engines. How do we name binary molecular compounds? When we look at the 2 nonmetals that we're going to be working with, the less electronegative element is written first. The more electronegative element is going to be written last. And remember, you can always go to Table S to determine the electronegativity of the elements that you're working with. The suffix IDE is going to be added to the name of the more electronegative element. So the one that is more electronegative, the one that is coming second, that is going to get the IDE ending. Very similar to what we would do with ionic compounds. One of the differences between naming ionic compounds and naming molecular compounds is that we're going to use prefixes to indicate the number of nonmetal atoms present within the compound. Important right here, little star right here. The prefix mono is often left out, omitted for the first element, but never omitted for the second. This is a common mistake that a lot of people make, but if we're using the IUPAC rules for naming these compounds, we're going to include the mono on the second nonmetal. So let's look at some prefixes and how we're going to use them to name our binary molecular compounds. Now, there's sort of a mix here of what you need to know and what's given to you on your reference tables. Remember Table P? Table P is that list of prefixes for organic compounds. Now, when we name binary molecular compounds, we're not going to use the first 4 on Table P. Instead, we're going to use different ones. And these you actually have to commit to memory. So for 1 atom, we're going to use the prefix mono. For 2 atoms, it's going to be di. 3 will be tri, and 4 will be tetra. If I had to identify a prefix that probably gives my students the most trouble, it's the tetra. A lot of people forget what that is. So that is something specifically that you need to know. So mono, di, tri, and tetra will be used as prefixes for these binary molecular compounds, and those you need to know by heart. 5 through potentially 10. 5 through 10 are going to be found on Table P of your reference table. So for 5, we're going to use pent, 6 will be hex, 7 will be hept, 8 is oct, 9 is non, and 10 is dec. If you look at some places in textbooks and on the internet, on different websites, You might see these referred to as penta, hexa, hepta, octa, nona, and deca. Depends on the situation and how the whole binary compound really comes together when you name it. So examples, examples, and more examples. Let's look at this first one here, CO2, very common binary molecular compound. So to name this, we'd look at the first element, which is carbon. Then we look at the next element, which is oxygen, and we'd notice that there are 2 oxygen atoms. So when we name this, we're going to put the prefix di and then put oxide. Remember that oxide right here tells me that that is the second nonmetal, and that is the more electronegative one. Notice there's 1 carbon here, no use of mono. No use of mono. So it's not monocarbon, it's just carbon. Let's look at this next one, PF3. So we're going to start out with phosphorus, and then there's 3 fluorines. So for 3, we're going to use tri, and then for fluorine, we're going to change the ending to IDE, so that would be fluoride. Now this next one, we just saw an example of this, a visual of this, so N2O4. Now our first nonmetal actually has a prefix other than 1. So we're going to start out by saying, well, I have 2 nitrogens here. So it's literally going to be di, then the nitrogen. We're never going to modify that first nonmetal name. Then we have 4 oxygens. So the 4, we're going to use tetra, and then oxide. And I did say tetra there, but really we would drop the A and just call it tetroxide. So this 4 right here is represented by this, and then the oxygen by the oxide. Let's look at the next one, NO, not no, that's nitrogen and then 1 oxygen. So now we have to use the mono, and then it's oxide. And we typically wouldn't say monooxide, it sort of blurs together, so you would say monoxide. Because there is 1 oxygen here, anytime you have 1 nonmetal as your second element involved in these compounds, you're going to want to use the mono. So there we have nitrogen monoxide. Let's look at our last one, SCl2. So S is sulfur, so we'll write that first. There's 2 chlorines, we're going to use the di. And finally, chlorine will change the ending to IDE, so chloride. Here's some basic examples of binary molecular compounds. So what did we learn in this little review? Well, we went over covalent bonding one more time. We defined the concept of a molecule again. We looked at empirical versus molecular formulas. We decoded the prefixes, looked at what you can use on table P and what you can't use on table P, and how we do represent the prefixes for 1 through 4. And finally, we wrapped it all up by naming some binary molecular compounds. Need more help? Feel free to contact me, and I'm always looking for feedback. Have a great day.